Hi, welcome back. In this video, we're going to do another least squares approximation example. In this one, we're going to use a linear relationship between logarithms of the unknowns instead of a linear relationship between the unknowns themselves. So let's look at the problem. It says in the table below, we have the estimated number of genes and the estimated number of cell types. So G is the number of genes and Z is the number of cell types for various organisms. We're going to use the method of least squares to find an equation relating the number of genes to the number of cell types. So notice that the numbers of genes are really, really big numbers. They're kind of impractical to work with. But we can work with their logarithms instead to make them a little more manageable. So I'm going to make a new table, the organisms and the number of genes and the cell types. Now, I'm going to use logarithms instead of the numbers that I was given. So I've got humans, worms, jellyfish, sponges, and yeasts. So for humans, it says the number of genes is 600,000. So I took the natural log of 600,000. I got 13.3. And the number of cell types was 250, so the natural log of 250 is 5.5. So I did the same for the worms. I did the same for the jellyfish. So I just took the natural log of each of those numbers to make my new table. All right. So now let's set up the equations. We're going to use C0 plus C1 times the natural log of G is equal to the natural log of Z. Instead of G and Z, we're just using their natural logs. So we're looking for the unknowns C0 and C1, and the equations we get are these. Using the numbers in my table, C0 plus C1 times 3.3 equals 5.5, C0 plus C1 times 12.2 equals 4.1, etc. I'm just writing all the equations that I get relating the natural logarithms of the values we were given. So we now have a 5 by 2, inconsistent 5 by 2 system of equations. So we're going to have a 5 by 2 coefficient matrix, and our B matrix is going to be a 5 by 1. Here's the coefficient matrix, A, and my B matrix, and the system we're actually going to solve is going to be the A transpose A times X equals A transpose B. So we need to get those matrices. So here's A transpose, and here's A. And now, when I multiplied these together, I got this, 2 by 2. And then for A transpose B, here's my A transpose again, and here's B. And when I did this multiplication, I got this, a 2 by 1. All right. So now we're going to solve the system A transpose A times X is equal to A transpose B. That will give us our linear approximation. Here's A transpose A again, multiplying it by the unknown vector X, and here's my A transpose B. And so when I solve this system, I come up with C0 is negative 3.7 and C1 is 0.7. So that gives me the equation natural log of Z is equal to negative 3.7 plus 0.7 times natural log of G. And we want a relationship between Z and G, right? So what are we going to do? All we have to do is use the natural exponential function to get everything back to where we want it. We want it in terms of z and g, not the natural log of z and the natural log of g. Let's exponentiate. I'm not sure if that's a verb, but that's a verb I use. Both sides of the equation. So e to the natural log of z is going to be the same as e to the negative 3.7 plus 0.7 natural log of g. And I can simplify the right side a little bit. So I get, on the left I get z, obviously. E to the natural log of z is z. On the right, it's e to the negative 3.7 times e to the 0.7 natural log of g. And 0.7 natural log of g, we can write that as natural log of g raised to the 0.7. And now e to the natural log of g to the 0.7 is just going to be g to the 0.7. So e to the negative 3.7 was 0.02, and e to the natural log of g to the 0.7 is just g to the 0.7. All right, so we have a relationship between z and g, and I'll see you in some other video.